Hello, and welcome to the talk on singularity maps of space robots and their application to gradient-based trajectory planning at RSS 2020. My name is Davide Calzolari. In the context of trajectory planning for robot manipulators, it is well known that kinematic singularities must be taken into account to avoid serious performance degradation. Let us consider a grasping operation in which a free-floating space robot must follow a given trajectory in inertial space in order to capture a target satellite. If a singularity is encountered, there will be significant deviations from the planned trajectory. This work addresses the analysis of the singularities for free-floating space robots, and it proposes to use this information to plan trajectory which are formally guaranteed to be free from singularities. For a free-floating system, the singularities are determined by the so-called generalized Jacobian. Unfortunately, this matrix has a complicated expression since it is a function of both kinematic and dynamic properties of the system. Moreover, we would like to obtain global knowledge on the location of the singularities. Therefore, advanced methods are required. The problem of determining and avoiding singularities is well studied in the literature. However, when considering free-floating robots with several degrees of freedom working in 3D space, the state-of-the-art methods which aim for an analytical solution to the problem are limited by the complexity of the generalized Jacobian. As of today, the problem of singularities is typically handled during the trajectory planning using numerical optimization techniques which attempt to avoid the occurrence of singularities. However, this method cannot formally guarantee that a singularity is not encountered. Therefore, we turn to rigorous numerical analysis methods. These algorithms allow computers to prove mathematical statements and obtain solutions with guarantees of completeness. However, the relevant state-of-the-art methods cannot be directly used to analyze the singularities of free-floating space robots. In this work, we present two approaches to determine singularities of free-floating space robots. The first one is based on interval arithmetic, while the second one on Taylor models. Both these methods provide guarantees on computation. A portion of configuration space is analyzed with these methods in a branch and bound fashion. The algorithm isolates regions of configuration space which can contain singularities from other regions guaranteed to be free from singularities. Unique properties of free-floating systems together with an additional heuristic are exploited to improve efficiency and provide feasibility of computation. The region where singularities might occur represents a conservative envelope of the singularity surfaces. We refer to these envelopes as singularity maps. These maps provide global knowledge on the location of the singularities. In the following, two examples of computation and utilization of these maps are presented. The first example involves a comparison of the interval arithmetic and Taylor model-based approaches for the computation of a singularity map for a 3 degrees of freedom planar robot. The resulting maps are depicted in the figures from different angles. The computation time of the novel approach based on Taylor models is less than 7% of the time required for interval arithmetic. Taylor models have a more complex implementation than interval arithmetic, but this result indicates that Taylor models are very suitable for this specific problem. As a second example, we provide the results of the computation of a singularity map for a 6 degrees of freedom space robot mounted on a 6 degrees of freedom body. The map is obtained using the interval arithmetic approach, and the figures depict various projections of the map. In the following, an example of utilization of the map for gradient-based trajectory planning is provided. We consider the problem where the value of the third joint must be minimized under the constraint that the minimum distance to the singularity map must be kept. It is shown that a safe distance to the map is kept during the optimization, thus the solution is guaranteed to be free from singularities. If instead an optimization scheme based on a constraint for the manipulability measure is utilized, an infeasible step which crosses a singularity might be performed, as it is shown in this example. This is the end of the presentation, and I will briefly conclude the talk. For the first time, a singularity map for a 6 degrees of freedom free-floating space robot was obtained. The novel use of Taylor models is a very promising approach to detect singularities with guarantees of completeness in an efficient way. We have provided an example of utilization of the map for a trajectory planning task. The main limitation of the method lies in its computational complexity. It is important to remark, however, that the analysis can be carried out offline, and it can be performed on dedicated parallel computing architectures. Future work will primarily focus on extending the method to handle the redundant case and improve the efficiency. Thank you for your attention.